Okay, for number 7, determine the kinetic energy flux of a 0.02 cubic meter per second of oil discharging through a 50 mm diameter nozzle. So we have here, we're going to determine the power. Okay, the power. Okay, we have P is equal to the discharge times the specific weight of the oil times the head. So, since Q is given, you can now get the velocity, which is equal to 10.186 meter per second. Okay, for the head, okay, from this formula, you can now 10.186 squared over 2 times 9.81 is equal to 5.288 meters. So, the power now is equal to 882 watts, or you can express this in HP. So, you can divide it by 746 watts to make it in horsepower. Okay, for number 8, a nozzle is attached to a pipe as shown in the figure below. The inside diameter of the pipe is 100 mm, while the water is water jet. So this is the water jet, that the water that is going that is coming out from the nozzle. Has a diameter of 50 mm. If the pressure at section 1 is 500 kPa, determine the water's jet velocity. So we will assume that the head loss in the jet is negligible. So here, since the pipe diameter is given, okay, pipe, okay, you have here section 1 and the pipe diameter. So you have here for at the jet, so you have also okay, you have 50 mm diameter of the jet. So here, this will be from using continuity equation. Okay, Q1 is equal to Q2. So you can get now the velocity 1 in terms of V2. Then, considering head loss, just get the energy equation from 1 to 2, then substitute values. Okay, so this is in terms of V2. Okay, so you can get now the V2. So the V2 is equal to 32.7 meter per second. So you have to remember that in this problem, the problem is being solved using continuity equation and the energy equation. For number 9, oil flows from a tank through 500 feet of 6 inches in diameter pipe, then discharging into the air. Okay, if the head loss from point 2 is 1.95 feet of oil, determine the pressure needed at point 1 to cause 0.60 cubic feet of oil to flow. Okay, so since the Q is given and the diameter is given, so you can get the velocity at point 2. Then here, you need to get the energy equation from section 1 and section 2. You have to remember that is oil. The liquid there is in oil. So your answer must be in oil. Then now you can get the pressure at point 1. no, at section 1. You can get the pressure at section 1 since the pressure at section 2 is exposed to atmospheric pressure, so that is equal to 0. Then the answer now, your pressure at section 1 is 8.04 pound per square inch. Okay, for number 10, okay, from the figure, a pump drawing a water from a reservoir. It discharges into the air at point B. The pressure at point E in the suction pipe is a vacuum of 10 inches mercury, and the discharge is 3 cubic feet per second. We are going to determine the total head at point A and at point B with respect to the datum at the base of the reservoir. So here, the given, okay, if this is your reservoir A and this is your reservoir B, so you have here your Q, so your pressure here, okay, is equal to 0. But here you have a pressure at A in vacuum, which is 10 inches in mercury. So since the Q is given, okay, for discharging, the Q is given, okay, PP pumps from reservoir. Okay, we have to list down the discharge or the given. So your Q is given. Then the area, okay, the diameter of the pipe is also given. So you can get now your VA. Okay, then okay, so the head of the vacuum is 10. So here, okay, what is the elevation? Okay, you have 25. So you can get the head at A. So the head at A is equal to this equation, P over gamma plus V1 squared over 2G plus Z. So since this is your P over gamma, and this is your velocity head, V squared over 2G, and this is your Z. So the head at A is equal to 14.14 feet. So since the diameter at section 2 is also given, and your Q here from section for pipe 1, no, if this is your pipe 1 and this is your pipe 2, the Q are equal, so you have 3 divided by the area of flow at pipe B. So since you already have your pipe, the velocity of pipe B is 8.59, so you can also substitute again, no, the formula of the head, this one again, to the equation. So you can get now the head at B, which is 81.15 feet. Okay, then I'm going to let you answer this one. Okay, these exercises, you try to answer this. Okay, that is for number 1, number 2, and number 3. This one, this is connected. Then for 4, 5, 6, okay, you try to review your the flow of fluid fundamentals. Okay, so try to review your fluid fundamentals problems, and you can use any study aid materials you have for this topic, and I hope you can answer this and you understand what we are discussing today. And thank you for listening. Okay, so see you on next meeting. Okay, we will try these examples. Okay, number 1, water flows through a 3 inches diameter of pipe at a velocity of 10 feet per second. Okay, find the volume flow rate in cubic feet per second and in gallons per minute. Then we also have to get the weight flow rate and the mass flow rate. In this sample problems, if you remember in your fluid mechanics, this was discussed in chapter 8, the steady and compressible fluid. So you can just directly substitute the values once you already get the formula. Okay, for example, for the volume flow rate, the formula is just equal to the area of flow times the velocity. And for the weight flow rate, the formula is just equal to the unit weight or the specific weight of the fluid times the area of flow times the velocity. And for the mass flow rate is equal to the density of the fluid times the area of flow times the velocity. Okay, for letter A, since here the pipe is considered flowing full, so the area of flow is just equal to the area of the circle. So you have pi over 4d squared. And since the problem asks you to get the volume flow rate in cubic feet per second and in gallons per minute, so you have to express your answer in the in cubic feet per second and in gallons per minute. However, for the weight flow rate in letter B and for the mass flow rate in letter C, there's no unit specified in the problem. So if you are going to answer also, this will be in Newton per second or in kilonewton per second. So it is acceptable because there's no specified unit in the problem. And also in the mass flow rate, if your answer will be in kilogram per second, it is also acceptable. Okay? For number 2, in the figure, the inside diameter of the pipe is 12 inches and 18 inches at sections 1 and 2. So your pipe is like this. So it is increasing, no, from 12 inches to 18 inches. And we let this one as our section 1 and this will be our section 2. If water is flowing in the conduit at a velocity of 16.6 feet per second at section 2, find the velocity at section 1. Then the volume flow rate at section 1, then the volume flow rate at section 2, then the weight flow rate and the mass flow rate. So you have so many things to be answered in this problem. So at first, you are going to look at what are the given values. So you have here the diameter at section 1 and diameter at section 2. So in that case, you can apply the first principle we had discussed earlier, which is the continuity equation, which is said that the mass flow rate in the path of flow of fluid in the pipe are equal. That the fluid that is going in, or the mass of flow rate that going or that enters the pipe is also equal to the mass of fluid that is going out of the pipe. So we have Q1 is equal to Q2. So in that case, you can get the velocity, no? Because here, the velocity at section 2 is also given. So you can get the velocity at section 1. So once you have now the velocity at section 1, so you can get the flow rate at section 2, which is equal to, okay, so they are equal. So the volume flow rate of section 1 is also equal to the volume flow rate at section 2. So next is to get the weight flow rate. So since you already have your velocity at section 1, so you can get now the weight flow rate of section 1. And of course, you can also express this in Newton per, that is weight flow rate. So, weight flow rate, that is supposed to be, this is pound per second. Or you can express it in Newton per second or in kilonewton per second. Also, for the mass flow rate, you can also express in kilogram per second. Okay, so because there's no required units in the problem. For number 3, okay, a gas flows through a square conduit. So you have here a square conduit, and the area of flow is just equal to the area of the square. So the area of the square, okay, so the side is 0.1, okay, this is the sides of the square, so the area is just equal to 0.1 times 0.1. So that is the area of the, okay, the area of the square. Then the velocity is 7.55, and okay, you have to take note that the fluid here is gas. No, you have to take note. Okay, so the density, you have to know the density. Then the, okay, so this will be yours. So your square conjugate, no? So here, 0.1 and at second point, okay? If this is the, okay, if that is the, so you have here, this will be your section 1 and this will be your section 2. So this is the cross section. Sorry, and it is increasing. So, okay, if this is, that is from 100. Okay, that is from 100. So, this is your section 1 and this is your section 2. So, this will be the cross section of your pipe. So here you have a small conduit. Okay, this is 0.1, zero point 0.1, and this is 0.25, and you have 0.25. Is that correct? Then the velocity at also given. The velocity is okay. V1 is also given, and the velocity of section 2 is also given. So now we are going to find out the mass flow rate of the gas and its mass density at the second fluid. So at the second point. So you have to remember that the fluid here is gas, and gas is a compressible fluid. So the density is not constant. So that's why the rho there, okay, the rho is not equal. So that's why you are going to get the density at section 2, which is in kilograms per cubic meter per second. Okay? So I hope you remember. So what are the points you are going to take note for number 3? So for number 3, you have to identify what type of fluid, if it is gas or liquid. For liquid, that is incompressible fluid, so the density are equal. For gas, that is compressible fluid, so the density is not equal. So you have to remember. Okay? For number 4, okay, I have to erase this one. For number 4, the flow rate of air moving through a square conduit, square duct is 0.5 meters by 0.5 meters. Um, the Q is 160 over cubic meter per minute. What is the mean velocity of the air? So since given the Q is given and the area of flow is also given, so what you have is Q over A. So the answer is this one. For 640 meters per minute or 10.7 meter per second. Okay. Then number 5, an 8 inches in diameter horizontal pipe is attached to a reservoir as shown in figure. If the total head loss between the water surface in the reservoir and the water jet at the end of the pipe is 6 feet, what are the velocity and the flow rate of the water being discharged from the pipe? Okay, so here we need to do energy equation from section 1 and section 2. So considering head losses, okay, considering head loss, again, total head loss between the water and the reservoir, okay, water jet is 6 feet. So it is said that the total head loss. So the difference, so the pressure head at section 1 is from here, from the reference datum is 15.5 feet. So here, the difference between the pressure head of section 1 and section 2. The pressure head at section 2 is equal to 0 because, why? Because it is exposed to since you discharge into the air, so there is equal, it is exposed to the atmospheric pressure, so this will be your head loss. So okay, so here just the total head at section 1 is just equal to the total head at section 2 plus head loss. So how the total head is equal to P1 over gamma plus P1 squared over 2G plus Z1. So at section 1, the total head at section 1 is P1 over gamma plus V1 squared over 2G plus Z1 is equal to the total head at section 2, which is P2 over gamma plus V2 squared over 2G plus Z2 plus head loss. So, P1, the pressure head is also equal, the pressure is also equal to 0 at section 1. Then the pressure at section 2 is also equal to 0 from the reference datum. So, what you have is only the elevation, okay? That is the elevation head from the reference datum of section 1 and the velocity head, okay? And the velocity head at section 2 plus the head loss because there is the velocity inside the pipe. Okay, so your V2 is 24.1 feet per second and your Q is equal to 8.41 cubic feet per second. So again, what are the principles here? The energy principles, the continuity principles, and those are the principles that we are going to use in these problems. For number 6, a turbine is rated at 600 HP. Okay, when the flow of water is 0.61 meter cube per second, then the efficiency is 87%. What is the head acting on the turbine? Okay, you have to remember that the efficiency is just equal to power output and divided by power input. Since the machine here is turbine, so what is the input power of the turbine? The input power of the turbine is the flow energy and the power output of the turbine is electricity. So what is the head? No? What do you mean by the head acting on the turbine? So you need to identify what power you are going to use, no? It is the power output or the power input. So you try to determine. So what is being asked here is the power input of that turbine. That is the input head, no? The input energy, okay? The input energy of the turbine, because the input energy of the turbine is the okay, that again, what is the head acting on the turbine? Okay, it is equal to 85.97 meters. So remember that the power input of the turbine is the flow energy. Okay.